All right, we had a question that we had for homework, guys. It was a question where we had a couple of funny angles that we don't like, we had to get rid of in order to find the total displacement or to find the sum of all of these vectors. So we got 1, 2, 3, 4, 5, 6, 7 vectors. We could have 1,000 vectors and still know how to deal with this. It just means a lot more work, that's all. 2 funny angles that we don't like, 2 funny angles that we got to get rid of. Once we get rid of those, it becomes a really, really straightforward question. So let's kind of off to the side up here, get rid of the first funny angle. We'll call it vector 4. Okay, vector 4 is going down like this at 30 degrees. We're going to draw our triangle around that. We're going to call this x, we're going to call this y. And we're going to label that as, should have been 300 meters, I believe, wasn't it, Brennan? 300 meters, yeah. Which side of the triangle is the x side? Is it opposite, adjacent, or hypotenuse? It's adjacent, so we're going to use the cosine function in order to find that. Cosine 30 degrees is equal to x, the adjacent side, over the hypotenuse. X ends up being equal to 300 times cosine 30. And when we multiply those two together, we end up getting 259.8076. We do the y component. Let's say sine 30 degrees is equal to opposite over hypotenuse. Opposite is the y side. Y ends up being equal to 150 meters when we do the math on that one. Okay, so the first one is done, the first funny angle. Then we have vector 5, and we have vector, sorry, I guess we missed one, right? Let's call it 6 still. We missed this one right here, right? It doesn't really matter because it doesn't really relate to what we're doing right now anyways. I just missed one when I was numbering it, okay? The last vector here that we're calling vector 6, it looks like this. We got 60 degrees right here. We draw our triangle around that 60 degrees, and we've got 300 meters right there. This is our x side. This is our y side. By the way, this 100 meters, some people look at that and say, well, I've got a 60-degree angle measured from that 100 meters. I've got to do something with that. I don't. Just because the angle is measured from that doesn't mean I have to do anything with it. Okay, which way is that 100 meters going? Straight down, right? There's no funny angle involved in that. Got a funny angle measured from it, but not measured to it. Okay? It's straight down as opposed to at the funny angle. So let's find the x and y components of vector 6 here now, Rutger. Yes, it is. Yes. Yeah, you're right. You're right. But we'll go through that process anyways here. We're going to say cosine 60 degrees is equal to, actually for the x component, we're going to use sine here, right? Sine 60 degrees is equal to opposite over hypotenuse, which is 300. 300 times sine 60. 300 times sine 60 is going to give me 259.8076 meters. We're going to do the same thing for the x component, except use cosine. Since the y component is the adjacent side, we'll say cosine 60 is equal to y over 300. Y ends up being equal to 150 meters. So as Rutger said just a second ago, the x and the y components end up having the same magnitudes of values. That's fine. Okay, that's fine. If you caught that and you were able to save yourself a little bit of work in the trigonometry, then that's great. If you didn't, then go through the work like we just did and get the right answer. All right, so now we've effectively replaced this one, and we've replaced this one with our x and y components, which makes our life a lot easier here now. Let's combine everything here now, x's and y's. The x component of the first vector is negative 400, neg 400 because it's to the left. The second vector is, tell me what the x component of that 100 is. Tara? 0, good. The x-component of the third one is, let's go back up there. What's the x-component of the third one there, Krista? Yes, good. It's positive 100 because it's to the right. This one is 0. This is the tricky one here. It's really the fifth vector, but we called it vector 4. The x-component is negative 259.8076. Negative because it's to the left. The next one is 0. And then the next one is positive 259.8076. The good news is, because, as Rutger called it, they're mirror images of each other, those two values actually disappear. Right? Negative 259 plus positive 259 gives me 0. Then the math becomes pretty easy to add in my head here. Negative 400 plus 100 is negative 300. Yep. I'm sorry. Actually, yes, you're right. They're both, yes, you're right. They don't disappear because they're both going to the left. You're absolutely right. Thank you. So we're not quite done there. We do have to pull out our calculators to do the addition there. Negative 819.6152. I think that's better. Josh, is that better? Thank you for that. For the y components, we are going to find that the y components cancel out here because one's going down and one's going up. For the first one, we're going to say that the y component is 0 because it's 400 meters straight across. For the second one, it's negative 100. For the next one, it's 0. For the next one, it's negative 300. 300 down, negative 300. For the next one, it's negative 150, right, because it's 150 down. For the next one, it's negative 100. And for the last one, we said that the y component was 150. And this one's upwards, so it's going to be positive 150. Now let's add all these up. Negative 400, negative 500. Now it's easy, right? Now we just take those two vectors, don't add them up. Okay, when I give you a quiz on this tomorrow, don't, and I say, excuse me, when I say find the sum of the vectors, don't do this and then say, oh, neg 819 plus neg 500 is neg 1319. Okay, we can't just add these up. We can't just add an x and a y the old-fashioned way. We've got to go negative 819 plus negative 500 gives me what? Well, I can find that by using the Pythagorean Theorem. When I give you this quiz tomorrow on this, that's exactly what you're going to have to do, is use the Pythagorean Theorem at this point. We get 960. The angle is going to be drawn here at the very beginning. Theta is going to be equal to the inverse tan function of opposite over adjacent. That's 500 over 819.615. We get 31.4 degrees. Anybody express that relative to something? 31.4 degrees, something of something, Josh? It's going to be south of west. We know that it's south of west because that angle is measured from the west axis, south from the west axis. Or you can look at it another way and say, well, to get to this spot from start to finish, we had to go west, then we had to go south. We went south after west, or south of west. Now, if you had drawn your diagram slightly different, which could have been correct, draw your diagram like this, 500 and then 819 over this way, you would have gotten an angle equal to, what would that have been, 58.6? Anybody get that? But it wouldn't have been 58.6 degrees south of west because now you're measuring it from the south axis. We went south, then west, or west after south, or west of south. Fraser, when you get 58.6, did you also say west of south? You said south of west?
No.
Okay. Okay. So be careful of that. Both answers are correct, but they have to be expressed properly. Not just 31.4, not just 58.6. It's got to be expressed with a reference frame here, south of west or west of south. And we've got to be consistent. If you draw this picture, you should have this answer. If you do this picture, then you should have this answer. Is that good? All right. I want to ask you a question here now. Let's say you're on that moving walkway at the airport. That moving walkway that moves forward at about 3 meters per second. I'm not sure exactly why they have those. You have to walk about 2 miles, it seems sometimes, to get you from security to your gate. And then they have about a 30-meter stretch where they save you the bother of walking. Like if they're going to put those moving walkways in, maybe they should put them in the entire way so I don't have to walk at all, as opposed to give me a quick little break. But in the end, they have them. Okay, whatever. Let's say that that moving walkway is moving at 30 meters per second to the east. Okay, let's say that I'm walking on that moving walkway. What did I say, 30 or 3? I meant 3. That would be a fast-moving walkway if it was 30. That wouldn't be a walkway. That would be a moving runway then, if it was 30 meters per second. That's about 110 kilometers per hour. That would get you to your gate quickly, hey? 3 meters per second to the east. So let me write that down. The walkway is moving at 3 meters per second to the east. Now, I'm walking. I have the capability of walking at 3 meters per second. Let's say I get on that moving walkway and I walk at 3 meters per second in the direction of the walkway. Okay? Can you tell me now what my velocity is relative to the walkway? How fast am I moving relative to the walkway itself? 3 meters per second. 3 meters per second east, right? I can't walk more than 3 meters per second. So if I'm on a moving walkway, if I'm on a walkway that's not moving, okay, it's broken down and it's not moving, and I'm walking at 3 meters per second relative to that walkway. If it's moving, that doesn't change what I'm doing. I'm still moving at 3 meters per second relative to that walkway. But can you tell me what my velocity is relative to the store over there, the convenience store that's beside the moving walkway? Okay, I'm walking at 3 meters per second on the walkway. The walkway is moving at 3. What's my velocity relative to that store? Okay. It's going to be 6 meters per second. That's the whole point of it, right? To let you go faster, to give you a little bit of a boost, to make you go faster. 6 meters per second. So my velocity here is relative. It's 3 meters per second relative to the walkway. It's 6 meters per second relative to the ground, relative to the store that's beside the moving walkway. Okay, my velocity is not the same with every frame of reference. Let's take this from a different angle here now. Let's say that I'm walking at 3 meters per second. I'm bored at the airport. I'm there 2 hours ahead of time. And I'm bored and I want to entertain myself, so I walk on the moving walkway opposite to the moving walkway. When it's moving east, I walk west. When it moves west, I walk east. Just to entertain myself a little bit. Let's say that I'm now walking at 3 meters per second on that moving walkway, but I'm moving to the west. What's my velocity relative to the walkway now? 3 meters per second. What's my velocity relative to that store over there beside the walkway? 0, right? Whenever we want to find a relative velocity, a velocity relative to something, we add them up. The velocity relative to that store beside the moving walkway was either 6 meters per second, 3 plus 3 gave me 6, or it was 0 meters per second. 3 plus negative 3 gave me 0. My velocity relative to something outside is just the sum of vectors. Well, what happens if I had some kind of situation like a river that's flowing to the east at 3 meters per second, but I was swimming at 3 meters per second that way, across the river? How do I find my velocity now relative to the ground? It's not a simple matter of 3 plus 3 or 3 plus negative 3. I'm still going to add vectors together, but now I have to add them together in 2 dimensions, using the analysis that we've learned over the last several days. Here's a simple example that illustrates what we just talked about with the moving walkway at the runway or at the airport. We got an airplane. This time it's outside the airport. We got an airplane that's traveling at 800 kilometers per hour east when the baseball is thrown inside of it at 100 kilometers per hour. Don't do this, by the way. Okay, this tends to raise alarms when you're on airplanes and you pick up a baseball and you throw it at 100 kilometers per hour at somebody. Okay, people tend to get upset when things like this happen on airplanes. I would avoid this. Okay, but let's say that somebody did do this. What's the relative velocity of the baseball? Well, the real question is relative to what? Okay, relative to what, and in what direction was it thrown? There's a whole lot of things that aren't clear in this question. The answer could be 100 kilometers per hour. The answer could be 900 kilometers per hour. The answer could be 700 kilometers per hour. It depends upon which direction I threw it, okay, whether I threw it to the east or to the west, or whether I want to find the velocity of the baseball relative to the airplane, which would make it 100, or relative to the ground, which would make it either 900 or 700, depending upon which direction I threw it in. So we've got to be very, very clear. We've got to be a lot clearer than I was when I asked you that. What's the relative velocity of the baseball? Relative to what? Okay, relative to the ground or relative to the airplane? And in which direction is the baseball moving? East, or is it moving to the west? Just like adding vectors together in 1 dimension when we want to find a relative velocity, 800 plus 100 is 900, or 800 plus negative 100 is 700. Okay, we got to add the vectors together to get the velocity relative to the ground. We're going to do the same thing when we're in 2 dimensions. But to add vectors together in 2 dimensions, we have to draw a vector diagram. It's not just a simple matter of 800 plus 100 is 900, or 800 plus negative 100 is 700. We have to draw a vector diagram and add them that way. Now, we're going to draw the vector diagrams the same way as we drew the vector diagrams over the past week. But this time, I'm going to differentiate something here. 2 types of vectors. 1, a solid line vector, and 2, a dotted line vector. The dotted line vector for us will be the resultant velocity. It will be the resultant vector. You're going to see why in a second, though, why I'm calling them solid line vectors and dotted line vectors. Now, we will have, every time we see a problem, 2 solid line vectors and 1 dotted line vector. We're going to draw a vector as a solid line. In other words, not as a resultant vector. If we're told that the pilot or the captain of a ship or whatever is aiming in a certain direction. Okay, what's the velocity of the airplane relative to the ground when there's a wind blowing to the west? Well, if the pilot of the airplane is aiming north, then the north vector would be drawn as a solid line. Question? No? If there's a river current to the west, but the captain of the ship is heading south, then that south vector would also be a solid line vector, not a resultant vector. The airspeed of an airplane, the speed in still air. In other words, I don't know about you guys, but when I get on an airplane, I always look at that book that they give you, that little magazine that they give you. At the back of that magazine, they list all the airplanes that they fly, and then they list the airspeed of these airplanes, and it's usually somewhere in the range of 800 kilometers per hour. Depends on the airplane. It's somewhere in the range of 800 kilometers per hour. Okay, that means without wind. The airspeed is without wind. So if you're told the airspeed of an airplane is 800 kilometers per hour, then we're going to make that a solid line vector. That's the speed of the airplane if there is no wind. If there's wind, it could be faster or slower. Okay, but that is not a resultant vector. It's a solid line vector, not a dotted line. It's a solid line. Finally, if there's a wind speed or a river current, the captain heads south across the river, but there's a current in the river that's 4 meters per second to the west. That river current is going to contribute to where the boat actually goes, or where the ship actually goes. If there's a wind speed that's to the west, but I'm heading north, I'm not going to end up north. I'm going to end up somewhere else. The wind speed is a solid line vector. Okay, it's not the resultant. It's not where I actually go. It's a solid line vector. It contributes to where I go. Wind speed, river current. Conversely, my dotted line vectors, or my resultant vectors, would be, for instance, when a ship or an airplane or whatever, a car or whatever, actually goes in a certain direction. So let's say we're told that an airplane is heading north, but there's a wind speed, and we don't know which way the wind speed is. But the airplane actually goes 13 degrees west of north. Where it actually goes is my resultant vector. It is my dotted line vector. Or where you want to go. It basically would say, if the pilot wants to go directly north, where does he have to aim? Where does he have to head? Well, we're going to assume that where he wants to go is where he actually does go. Therefore, the solid line vector would be where he aims, where he heads. The dotted line vector would be where he wants to go, or where he actually does go. And finally, if we're ever looking for the velocity relative to the ground, that's going to be my resultant velocity as well, my dotted line vector as well. Here's the rule of thumb. If it contributes to the actual velocity, then it's a solid line vector. It's not a resultant, right? If it contributes to it, it's not a resultant. If it is the actual velocity, then it is the resultant. It is where we want to go. It is the dotted line vector. So if you're ever given a question and you're not quite sure how the wording matches up, whatever, just take a step back from it and say, okay, is this vector where I'm actually going, or is this contributing to where I'm actually going? If it is, then it's dotted. If it's contributing to it, then it's going to be a solid line vector. Give you a nice straightforward, I think, straightforward example here. And we'll wrap it up. So it says the pilot of a plane heads directly north to Edmonton at a velocity of 200 kilometers per hour. However, there's a wind of 50 kilometers per hour blowing to the east. Where does the plane actually go? We've got two vectors here, two vectors given to us. 200 kilometers per hour to the north and 50 kilometers per hour to the east. Can you tell me, are those solid line vectors or dotted line vectors? Are they contributing to where I'm going, or are they where I really am going? What do we got there? Sorry? Dotted line? Dotted line vectors correspond to where I actually go. So are these going to be dotted line vectors? Let's think about this, guys, okay? We're not going to draw the picture right away, okay? Let's just visualize it. I'm heading north, but there's a wind that's blowing me to the east. Do I actually end up going north? No. I end up going somewhere northeast, right? So these two vectors aren't where I actually go. These two vectors both, in concert with each other, contribute to where I go. Okay, one's north, one's east. Where do I end up going? Somewhere northeast. That's my dotted line vector. These are going to be solid line vectors because they're contributing to where I'm going. If we go back to that wording and that table that I gave you, if you aim or head in a certain direction, that's a solid line vector. The pilot heads north at 200 kilometers per hour. That's a solid line vector. Notice it's a velocity vector instead of a displacement vector, but that's okay. We have another one that's a wind blowing at 50 kilometers per hour to the east. I'm not going at 50 to the east, but the wind is contributing to where I actually go. Wind blowing. If we go back to that picture again, or to that table again, wind speed is a solid line vector. 50 kilometers per hour to the east. How do I combine these two vectors? How do I put them together? Same rules as always, right? Front to back. I can draw the 50 kilometers per hour here. Or I could have drawn it like this. Either way would be perfectly acceptable. Now my resultant vector, where the pilot actually goes, is my dotted line vector. It's the one that goes from start to finish. This time, instead of solving for displacement, I'm solving for a resultant velocity, where the plane actually goes. V is going to be the square root of 200 squared plus 50 squared. Doesn't matter which diagram I'm using, we still get the same value. I end up getting 206, or 2.1 times 10 to the 2 kilometers per hour. So the plane actually goes, look, the plane in still air could go at 200 kilometers per hour. But it's actually going a little bit faster than that because the wind is helping it along here, right? That's why flights one way across Canada going east tend to be quicker than flights going west. You ever fly to Toronto, your flight to Toronto might be about 3 hours and 45 minutes. Your flight from Toronto to Calgary might be about 4 hours and 15 minutes. Why the difference? No, it's not actually. No, it's not. It's prevailing winds. The winds are usually blowing from west to east, which speeds us up going east, slows us down going west. Hold on for 1 second, Fraser, okay? Let's find the angle here. The inverse tan function of opposite over adjacent, 50 over 200. Let's get that value. We get 14 degrees. 14 degrees west of north. Or if we had it under here, we would have gotten 76 degrees north of west. So where does this airplane actually go? Well, it goes at 205 kilometers per hour, 2.1 times 10 to the 2 kilometers per hour. Not north like we were aiming, but rather 14 degrees west of north. You can see how this might be, Travis, sit down please. You can see how this might be kind of practical if you're a pilot. It might be useful to know when you aim in a certain direction where you're going to end up going. Or even more importantly, if you want to go in a certain direction, where you have to aim, which is exactly what we'll do tomorrow.